Okay, so let's try a slightly different example, which will sort of motivate. Suppose you and I have this great scheme. We're going to run over to Bank of America, and we're each going to stand in front of a machine. We're going to each try to take $50 out of the 6004 account. And the bank has carefully written some code that does this. You take an account number and an amount, and the bank says, well, this is great. We're going to pick up the balance and subtract the amount you're trying to withdraw and put it back in the balance. That all is great. And what the bank imagines will happen is that there'll be a process that's dealing with the first ATM and a process that's dealing with the second ATM. And there's a sort of notion that fine, you do your transaction, and then I'll do my transaction, and these two programs run, and everything is fine, and we end up subtracting 100. However, if the execution of the program interleaves in the wrong way, in other words, if we stop running process 1 on the bank's big time-sharing system right after it's loaded the balance, and then process 2 comes along and handles my transaction before we completed your transaction, you can see what's sort of happening here is that I'll subtract $50 from the account, but you'll subtract $50 from the account when your process resumes execution, but you'll be using the old balance. Right? So in the end, we'll end up with $100, but the bank will think that the account has only had $50 subtracted from it. All right. So I think we should all do a field trip right now and see if Bank of America has attended lecture 21 in 6004. Okay, or at least the people they bought their database from. Okay, so what is it we actually want to have happen? What is it we want to guarantee? What's a simple way to guarantee that we never have these bugs? And the simple guarantee that we want is the notion that once I start executing these 3 instructions, we load the balance, we manipulate it, and we restore it back. Those run as an uninterruptible unit. No other program is allowed to start manipulating the balance. Read it, write it, do anything to it, okay, as long as I'm manipulating the balance. The balance, in some sense, is undergoing some amount of change by process 1, and it doesn't want to, either the change should not have started, or the change should be completely finished, and no one should be allowed to mess with the balance in between. Right? That's how we're going to guarantee we can't both sneak out $50 at the account and end up richer than the bank is sort of going, well, this money, and it's all in the 6004 account too. I don't understand. So, okay. So modern systems, they implement the so-called transaction semantics, which sort of guarantees the atomicity of a sequence of operations. It turns out we can use semaphores to implement that semantics. So what we have here is, here's the code, and we want to add some semaphores to it. And what we notice is that we want to have a different sort of precedence relationship, which is that A and alpha either happens before beta or beta happens before alpha, but they can't happen concurrently. Right? We definitely want one to happen before the other. We're not particular about one before the other, and in fact we don't want to introduce the constraint that alpha always happens to happen before beta. We would like to have the flexibility of them happening in either order, but we don't want to have them happen at the same time. And so what we're going to do is we're going to introduce this notion of a lock, a simple semaphore that gets initialized to 1. So this might be a binary semaphore. Binary because the value of this semaphore is either 1 or 0 at any given moment. And so think of this as a resource we're managing a single resource, which is the right to be in this chunk of code. That's the resource we're managing, the right to run these instructions. Right? And we're going to allow exactly one person to have that right at any given time. Think of it as a token. I'm going to hand out the token, and I have to wait until you hand it back before somebody else can run. Okay, so we wait on the lock, we do whatever we want, and now if everybody who touches balance waits on the same lock, no one will be manipulating the balance, okay, without having first acquired the lock associated with this balance variable. Okay, and then when we're done, we signal, which means we'll free up the opportunity now for someone else to potentially manipulate this. Okay, so access to a critical section of code that we want to make sure runs without any possibility of other people who want to manipulate the same piece of shared memory getting in and sort of starting when I'm only halfway through. This is what's called mutual exclusion, okay, or the notion of exclusive access. Only one of us can be running the code at any given time. An interesting question is, if you were Bank of America, what sort of lock should you have? Should you have one lock for, all of Bank of America? Right, what would be the problem with, having one lock? Every time anybody in the whole world manipulated an account, somebody had to say, I have the account manipulation lock. Well, yeah.
There's probably millions of Bank of America customers.
Right. So what you're saying is, well, that produces a lot of unnecessary precedence constraints, right? The trouble is, by locking everybody out of all their balances, I'm not manipulating all the balances, I'm only manipulating one balance. Okay, what about a lock per account? Well, that would get the job done, but it's a lot of locks, so that might be, in a sense, expensive. And then maybe there's intermediate things. Where we might have fewer than one lock for everything, but not, rather than have everybody have their own lock, every account have their own lock, we might have a lock for all the accounts that are, were originated in the Bay Bank down the street here, or something like that. So it cuts down on the number of locks a lot. There's actually a famous example of a global lock that has wreaked havoc with people's plans to run concurrently. It's in Python. Python has a global lock, so whenever you're about ready to manipulate things in Python that will cause the state of some data structure to be inconsistent for a moment, you acquire this global lock, which is fine when there's a single program running, but if you try to run multi-threaded in Python, you spend almost all your time waiting on the stupid global lock. So global locks in Python have, are an example of a convenient, remember a moment of convenience, a lifetime of regret? Well, here we see it again, sort of cropping up.